Okay, so we'll go ahead and get started. And from yesterday's presentation, look at what we have here, okay? Because when you had left yesterday, what did this look like? It was just the whole solution was yellow. So what had happened is the potassium nitrate, is that on the bottom? No. Remember, all nitrates are soluble. Okay? So we got a potassium nitrate solution on the top, but then on the bottom, it's lead, because, no, it's lead iodide, because all iodides are soluble except lead, mercury, and silver. And we could actually disturb this. I don't want to spill any either. Get enough centripetal acceleration, centripetal I mean. Okay, so if we were to, like I had mentioned, try to slightly disturb this. Looking for, here we go. Just take parts of these tongue depressors and just take this and stick it in here and swirl it around. And then, now we have our yellow precipitate again. And now we'll just leave it set here, because this is what it looked like yesterday, correct? All right. Okay. So, page 309. And there's sample problems that you can look at. And these books can be taken from this room. They're not confined to this classroom. Okay? If you feel that could benefit you, you're more than welcome to take some of these books out of here. So like we had mentioned, they've got all sorts of these sample problems. But practice problem number 1 on page 309 says, oxygen was discovered by Joseph Priestley in 1774 when he heated mercury to oxide to decompose it to form its constituent elements. Okay. So it's saying we've got mercury to oxide, which we know is this, and what? No. Mercury to oxide. Okay. We said little 2, now oxide. Okay. Yes, in page 309, practice problem number 1, oxygen was discovered by Joseph Priestley in 1774 when he heated mercury to oxide to decompose to form its constituent elements. Okay, so we need mercury to oxide. We've got our mercury, and the 2 you say here, which is not correct. Okay. Gesundheit. So then what is oxide now? Okay. Do we need to change anything here? Okay. So then this is in a solid form, mercury to oxide. Okay. And don't get bent out of shape about a lot of these. You will be, let's say, notified or informed when we would want you to do that. Probably when it's going on the product side. I mean, this is difficult enough. We don't need to keep adding more and more difficulty. We know this is hard. It's supposed to be hard, because if this was an easy class, the rest of your classmates would be in here, wouldn't they? Yes. 309. Okay? So then, if this is decomposing into its constituent elements like it states in the problem, and is this written correctly? Yes, because this is -2, that's +2 because it says mercury 2. So if this is decomposing, okay, so now we've got Hg, which would, we're going to say is a solid, plus O2, which what would we put in there? Yeah, it would be a gas, okay? But if we really wanted to be specific, when you do look on the periodic table, what do you notice about how mercury, or Hg, is written on that table? It's the same on your table. It is not, okay? But when you look over here, what do we notice about the writing? It's blue. That must be significant when all of the other elements are either written in red, black, we see blue, and then some of them are clear, like technetium. Just use that as an example. So then the reason we say that is mercury is actually a liquid, but we're just going to say that this is still just going to be a solid, okay? So we know that a chemical reaction really has taken place because we've got this is being released, okay? And I think it was one of your A and P classmates that was saying that, talking about arrows and things like this, sometimes maybe you're required to do that, okay? We're not requiring you to do that. This is just saying that oxygen gas is being released. That's all that arrow really means. So will you encounter that in college? Maybe, but that's really all that it needs or means. Okay, what about this reaction now? Is it balanced? It is not. Okay? Okay? All right. So therefore, it says in part 1, how many moles of mercury 2 oxide? Okay? Here's our mercury 2 oxide. It's saying how many moles? Well, of course, if it's asking for how many, well, we don't know what that is. That's what we're looking for. Okay? Then it's saying are needed to produce 125 grams of oxygen. Okay? So just because you're on the product side, that doesn't mean that we can't come back to this side, because we just need to know how much we're actually starting with. Because if you remember from way last August, maybe September, okay, what was it? Elephant's toothpaste? Yes, I think that's what it was. You needed to have something, a solution of, I think, of that, okay? But we wanted 0.10 molar Ki, okay? Do we happen to remember what molar means? That means a certain amount of moles of a substance per liter, okay? Since we were learning about moles back then, that was a practical place to perhaps throw that in and do an activity over. So that's what we did. So it's important to know, well, how many moles of this do we need? If we know we need 125 grams, well, how much do we need to start with in moles? And that's what the question is asking. All right. So the only place we can start is with what? Yeah, we can't start here because that's unknown. The reaction, doesn't really help us, but with our number here, that's the only place we can start. We have 125 grams. Now, don't do this, okay? The information that I'm putting up here, it's not that it's inaccurate, but once we do this, we know we're going to change this to moles, and then if we do this, what do you think is wrong with that so far? because oxygen, just like helium, or excuse me, just like hydrogen, I mean, chlorine, any of the halogens, and nitrogen, they're all diatomic. Because if you do this, or we're an individual who just does this, and maybe they just put grams down here, I don't know. How do you know what you're measuring? I wouldn't know either. And sometimes students ask questions and they say, well, I don't know what to do next. Well, my response is, if you're not going to help yourself, I certainly can't help you. Okay? So therefore, grams of O2. Therefore, anytime you encounter that, we know we're going to put 32 here instead of 16. Okay? Now, that was different when you're doing composition stoichiometry, because you're just only dealing with one compound. Here, you're starting on this side and coming back to this side of the equation. That's reaction stoichiometry. And we read about that at the beginning of this week. Okay? So these have canceled. We're in moles of this substance. But what is significant about a mole ratio? It allows you to change what we have, okay, which is this grams of oxygen, and change it into what it is we're looking for. But in order to do that, how do we cancel these moles out in our next step? Okay, so for every mole of O2, okay, we can jump from that side of the equation to this side, because our final step here is to put what on top? Okay, so we're looking for moles of HGO, mole to mole ratio. Look back to our equation. There's a 2 in front of there, so we have to put a 2 here. Okay, everything has canceled. You're left with moles of mercuric oxide, and that's why we write this up here. It's saying how many moles of this? Well, now we're in moles of mercury oxide, so we know that we're done now. Okay, so then the last thing that you would do is multiply across. 125 times 2 divided by 32, and you should get 7.81. Okay. Okay. And and then let's see here. All right. So now, yes, we had our. Oh, okay. So front row, we on the bus here. Back row. Okay. So then, does that mean should we move on to the second one? Okay. Which we can do. All right. So now, we don't have to totally reinvent the wheel here, because in the second problem, it says how many moles of mercury are produced. Okay. Well, we still have 125 grams. Well, how many moles of this? Okay. Now, keep in mind, just because these coefficients are yes?
You told us that, like, we get told that HGO is like a solid, like we'll get that information?
Yes, that's correct. Okay. So we can't just say, well, it must be 2, because there's a 2 here. Okay. That would be bad information, because this is just a counting unit. Okay. Just like the example we give is if we needed to work on the desk that this computer sits on, okay? What is the difference between is there anything different between those two numbers? Because it gives you the same length, okay? So if we take every 12 inches is a foot, so if we take that times 8, 8 times 2 gives you what? No, I could have swore I heard 10. Okay, 8 times 2 gives you what? There's our 6 for 16. Carry your 1. 8 times 1 gives you 1. Carry it 96 inches. So, if you have to be dealing with lengths, do you want to deal with 96 or 8? You'd probably want to deal with this because the counting unit is much, much smaller. And that's all that it is. It's just a counting unit. Okay. We still have 125 grams of oxygen. Okay? It's still going to be 32. It's still going to be a mole of this. The only thing that would be different, and we can show you 125 grams of oxygen. Okay. I don't know how well it shows up all right. We know that for every mole of O2, you get 32 grams of O2. Then for every mole of O2, we get a mole of mercury until we look back at our equation, and what does this tell us? We have to put a 2 here. And we don't even have to punch this in our calculator. Why not? It's the same thing. Because 125 times 2 divided by 32, you're going to get the same answer. 7.81. Okay. Back row. Are we okay? Okay.
Are you always going to get the same answer?
No. No. It's because that just happened to have the same coefficient.
Okay, so you get the same thing as like the first multiplier.
That's correct.
What's different about that one? Nothing.
Just a different substance. We're looking for this one in problem 1. We're looking for that one in problem 2. That's the only difference. It's going to give you a different substance. In other words, 7.81 moles of mercury only instead of mercuric oxide. That's the only difference. Okay, so look at what we have here. See, it precipitated back out again. We got a clear solution on top and a precipitate on the bottom because we had just shown this earlier. It was nice and cloudy. Okay. If your cat is thirsty, here's a solution for him. Oh, sure. Your cat probably won't fare too well with that. Yeah. Don't give them that. That would not be good for them. Okay. So just a moment here. Okay. So what we can do, all right, is okay, one of those two. Pick. Okay, so a single replacement reaction. Well then, let's see here. If we have aluminum chloride. No, scratch that. If we have hydrochloric acid, okay, then give us a metal. Lead? Okay. And I know why you picked that. Because you're already 3 steps ahead of everybody else. Why did your classmate pick lead?
Because it's insoluble to something.
Okay. So then if we take this hydrochloric acid, okay, well then we can add some lead, okay? And this was probably, could be also a trick question, because we'll say that this is an aqueous solution. That would have to be given. Okay, this would be a solid. So then in this reaction here, okay, what does this lead do, because you had picked a single replacement? Okay, so we've got Pb. So this lead has replaced the positive ion here, +1, -1. Now you just have to say, was this plumbus or plumbum? I don't expect you to know that. Plumbus or plumbum? Okay? Because if you did plum, what, I see now I can't remember. Plumbus or plum, you said plumbum. Plumbus would be perhaps +4, but that's why it has these abbreviations, because plumbum is Latin for lead, and that's why it's called Pb. Okay? And then if that's a +2, chlorides -1, and then what's left over? And it's a gas. Okay? So we really could have picked any metal. We just let you pick one. But here we know that this aqueous solution precipitated out. Okay? Because you pick any other metal, okay, you're just going to form a solution. It's going to be an aqueous solution. But the reaction is still going to proceed because you have a gas coming out of there. Okay? It doesn't, this having a gas or a precipitate out like what we saw there is evidence that a chemical reaction is taking place. Okay, so now we need reactant or product side. Reactant side, okay? So how many grams of this do we have? A random number. 84 is the first answer we had. So 84 grams. We want to know, well, in this reaction, well, how many moles of this are going to be given off or given away, whichever. Do you want to try this on your own? Yes. Okay, so I'll just go ahead and hit pause. So just to point you in the right direction, what's the first thing that you should do now? True, you should balance it first. Well, you can go ahead and start the problem, but you're probably not going to get very far unless you're lucky enough it's a 1-to-1 mole ratio. Okay, we'll hit pause now. Okay, so first thing we need to do is balance this reaction. We've got 2 chlorines over there and only 1 here, so we have to put a 2. Okay, and then lead is 1-to-1, chloride is balanced, and hydrogens are balanced. Okay, so therefore, even if you didn't balance this, you would have been okay because it's a 1-to-1 ratio. Okay, so what we mean by that is the only place that we can start is with 84 grams of lead. And what are we going to change this grams of lead to? Okay, so for every, 227.20 grams of lead, you get a mole of lead. Now, if you remember from last Monday, all we were doing was mole to mole problems. Those are 2 steps. Mole to mass is 3, mass to moles is 3, and here in a few minutes we'll do mass to mass, which will be 4 steps. Okay, so for every mole of lead now, we have canceled these. Now, we want to be able to jump from this side of the reaction to this side, okay? So therefore, how do we cancel out this mole in our next step? Put it on the bottom. We want to convert what we have into what it is we're looking for, which is what? Okay? So remember, when we're doing that composition stoichiometry, we had said this 3rd step is so important because it allows you to change what you have into what it is you're looking for. Now, is there any coefficients there? No. So all we have to do is take 84 and divide by 207. And you get 0.41 moles of hydrogen. Okay? That's true. But that's when you're looking for a mass, though. Okay? That's what's different from the composition stoichiometry. Yes, I agree. You would have to compensate for 2. If we were looking for a mass of that, then that would be important. All right. Back row. Okay. Okay, front row. All right. Do we move on ahead to page 311, or do we need to see another example of this? I don't think so. No. It's going to be one more problem. It's either going to be a 3-step one or a 4-step one. Okay. So then, okay, it'll be just a moment here. So this could be an example where you have to be provided this information, okay? Because you can put these in here, and we know that this will dissolve. We know that this will dissolve, one, because we're telling you that, okay? So in this double replacement reaction, all of the subscripts are provided as needed, okay? Are any of those subscripts going to that side for sure? Because we have 1, 2, 3 subscripts. Are any of them going to that side for sure? The 3 is for sure. And maybe the 2 for this and this, we'll just have to wait and see. So, we need the charges here. Chlorine is negative what? Or chloride, I should say. Magnesium. Now you might say, why are we doing this if it's already balanced out? Well, we need to get to that side of the equation. Carbonate is negative what? And sodium. Okay, so they all add up to 0 now. Okay. Will this reaction proceed? Let's go ahead and see once what happens. And I always suggest start with your negative ions, because when you're dealing with these, you don't know for sure what positive charge is going to be. That's why we always say start with your negative ion. Okay, but now we need to start sodium or magnesium. Which one do you want to start with? Magnesium. So what does magnesium bond to but on that side of the equation? Okay? And we'll come back to that. What does sodium bond to? Okay. Now, we had two aqueous solutions, just like what we would have done yesterday, and poured one in, doesn't matter, this way or this way. Let's look at our rules, okay? What do you think about chlorides? Are they soluble? They are extremely soluble, except lead, silver, or mercury. So it's not bonding to any one of those. So it's going to stay in an aqueous solution. Okay? Remember, the charges will not change. But what about our magnesium? It says, our carbonates. They are all insoluble except for, and who are alkali metals? Column 1. Is this in column 1? It is not. So this is an exception. So does this stay in an aqueous form, or does it fall out as a insoluble precipitate? It's going to fall out. It's insoluble. Okay? So this reaction will proceed. Okay? So this is a reaction that will take place. Okay. So now, we need reactant or product side. Okay? So now, do you want grams or moles? Okay, so which one? Okay, so we're going to say 0 point what? How many moles? 0 point, okay, 0.57 moles of magnesium carbonate. Okay, so now we want, if we want 0.75 moles of magnesium carbonate, which one of these grams do you want to work with? Okay, so then how many moles of this would be required? Okay, so we only have, I'm sorry, not moles, X amount of grams. There we go. I was trying to write and talk at the same time and it just wasn't working. Do you want to try this on your own? Okay, I'll go ahead and hit pause, and you can work on this. Okay, we'll go ahead and get this rolling. If we had 0.57 moles of magnesium carbonate, that's what we're starting with, how many grams of this sodium carbonate would be required? Well, we canceled all our moles, okay, and we changed it from getting to this side of the reaction to this side in this mole ratio. Is there any coefficients that belong here? There is not, because it's a 1-to-1 ratio. So moles of magnesium carbonate have canceled. We've got moles of sodium carbonate and these moles of sodium carbonate. Therefore, we would have to add together, let's see here, 23 is 46, 12.01, and then 48. 106. Okay, so that 106 goes here, and you multiply them together, and we get how many grams? .57 times 106. 60.43. So 60.43 grams of sodium carbonate. Okay, that's all I have. We'll catch up to you next time.